Okay, so let's talk about geologic time. So a lot of this class kind of deals with this aspect. I mean, there's kind of a lot of important chapters in this class, but you can make the argument that this is possibly one of the most important because this is kind of what rocks really tell us about. They tell us about what happened through time in the past, and this is actually a very special place regarding sort of the history of geology and how the science was born, these sedimentary rocks that you see here that we'll talk a little bit more about. So this is an image of the Grand Canyon. We've looked at it before. We'll discuss kind of what these layers kind of mean, and we'll talk about how we can sort of date things. There's sort of two different elements to geologic time. There's relative time and there's absolute time. But the kind of a Grand Canyon is a great place to kind of go and kind of see, just the changes through time and the represented in the rocks. But the deal with geologic time and what so many people struggle with are the huge numbers that are involved with geologic time. And in general, people struggle with big numbers. I can, say 10, and you can visualize how many 10 is. You've got 10 fingers, okay, there's 10. I know what 10 looks like. If I say 100, you can maybe visualize about how much 100 is. If we got 10 people in the class to hold up their hands, say there's 100 fingers. Okay. But beyond that, beyond numbers of like 1,000 or maybe even 10,000, when we start talking about millions or tens of millions or billions or tens of billions, your brain can't really wrap itself around those numbers and what that looks like. And geology actually gives us an opportunity to launch into that. I think it's just a good science, it's a good subject to really help yourself visualize these numbers, because these big numbers, they're not just in geology, right? They're in other areas of life. When we talk about millions of dollars or billions of dollars or even trillions of dollars being spent on taxes and things, you want to be able to recognize what those numbers really represent and what they mean. There's about 350 million people in this country. That's a lot. That's a lot of people. How much is it really? If a million people do something bad, well, there's 350 million people in this country. That's not even 1% of the country. It's less than 1%. Is it really that much? It's those big numbers that you kind of have to conceptualize. So let's just try and work with this. So let's take the idea that let's assume you live to be 100 years old, right? Maybe some of us will get to be 100 years old in this class, maybe not everybody. But to experience 1 million years, you need to live 10,000 lifetimes, right? You need to live to be 100 10,000 times. Well, I can show you what 10,000 looks like. There's 10,000 little army soldiers. Every little block is about 25. So imagine each one of these little guys as you living to 100. If you lived to be 100, this many of these little dudes times, then you'd live for 1 million years. And 1 million years in geologic time really isn't even all that long when we're talking about a planet that's 4.5 billion years old. I mean, the dinosaurs died out 65 million years ago, right? So this many little lifetimes only gets you 1 million years back. You'd have to do this whole room 65 times if you follow along with me. That's a lot. So we can sort of conceptualize these big numbers sort of by just kind of taking it piecemeal at a time. Well, I know what 10 looks like. Okay, I know what 100 looks like. I know what 1,000 looks like. If you imagine a stadium of people, maybe that's 20,000. You can start to get an idea of about just really the size and the immensity of these numbers and just how long deep time is. And when I say something, as a geologist and as a paleontologist, talk about the Ice Age. The Ice Age only happened 10,000 years. We came out of the last Ice Age 10, 11,000 years ago. And to you, the Ice Age may seem like it was some time period way longer time ago. Oh, the woolly mammoths, they're fossils and they went extinct a long time ago. Well, not really, not when we compare it to Tyrannosaurus rex, which went extinct 65 million years ago. The time of the dinosaurs was so much longer ago than the ice ages. And in my mind, the ice ages happened yesterday, but the age of the dinosaurs in my mind happened before I was, you know, born, obviously. But just kind of using relative comparison. Anyway, so a million years, it's a long time ago, but geologically speaking, it's really not that long ago. So, how has geology dealt with time? Like, kind of what's the history of geology? How have we ended up, thinking the world is 4.5 billion years old, or understanding the dinosaurs were died out 65 million years ago, or even knowing that the ice age ended about 10 to 12,000 years ago? So let's, kind of tell the story. So let's back up. Let's kind of turn this into a history class. The big question always that has kind of plagued people is how old is all of this? We know how old each other are. We know, we keep track of our birthdays and how many times we go around the sun and all that. But a big question in science and in just humanity throughout history in general was, how old is all of this? How old is the Earth? And different cultures have come up with different answers. But, how old is this rock? As a geologist, people ask me that. How old is this thing? How old is that? But generally, the big question is like, how old is the Earth, right? How old is all of this? Well, kind of the first stab of it was kind of based upon. Well, I don't want to say the first stab at it. Western culture and Christian-dominated cultures took a good stab at it prior to the 19th century, and they came up with a biblical view of about 6,000 years old. And based upon the knowledge that they had, which their lives kind of revolved around Christianity, A for effort. You're asking that question. You're trying to put a number on it. Different cultures, though, like the Chinese Hindu, basically just said it's old beyond comprehension. Well, turns out that seems to be pretty accurate, because I can barely comprehend 4.5 billion years. But let's talk about this kind of first stab if we're going to sort of take the European view of this. There was this guy, and his name was Bishop James Ussher, and in about 1650, he kind of went through the Bible, and I'll just kind of read the little quote here. Annals of the Old Testament deduced from the first origins of the world, the chronicle of Asiatic and Egyptian matters together produced from the beginning of historical time up to the beginnings of the Maccabees. If I said that right. And if you're a biblical scholar, you'll actually understand what some of that meant. But basically kind of went through the Bible and sort of tried to piecemeal what he knew about history and kind of the statements made in the Bible to try to come up with an age. And what he deduced was the entrance of the night preceding the 23rd day of October. So if your birthday is on the 23rd of October, in fact, I wonder if we have class on the 23rd. Maybe we can celebrate this. Year before Christ, 4004. So when you hear people talk about the Earth being only 6,000 years old, it was this guy that kind of came up with it in 1650. And some people may, I don't know, kind of poke fun at that, and some people still believe that, and that's fine. But this is kind of where that came from, and it's great that somebody started to ask the question, how old is all of this? And let's look at the knowledge that we have to try and answer this. This guy, I'd argue, was a good scientist. He was taking the knowledge he had around him, the observations he had around him, and just tried to apply it. Fast forward into the future, and we have this guy named James Hutton, who's generally regarded as the father of geology. And he said the solid parts of the present land appear in general to have been composed of the productions of the sea and of the other materials similar to those now found upon the shores. And you can read that, and you've now understand sedimentary rocks and how they're deposited and formed, and you realize he's probably talking about sedimentary rocks. He saw some rocks on the beach and said, hey, wait a minute. This is an old beach. And there's a little picture of him. Oh, look, he's holding a rock hammer. Cool. So, James Hutton, this is kind of where he made his first observation of this place called Sycar Point, and it's in northeastern England, and he saw these rocks. And if you get up close to these, I think these had fossils in them, and he started to realize wait a minute, this is old bottom of the ocean. This is old beach sand, maybe. And he started to see the similarities between this and what he kind of sees out in the more active world. And we can kind of take this and draw it, and you can see the sedimentary layers here, the top layers and the bottom layers, and we'll come back to this a little bit later. Lots of words. So this is what he said, and I kind of want to read this to you. I think it's fairly important because what a realization. This is sort of like the birth of geology as a true science. And it's still relatively recent compared to a lot of other scientists, or a lot of other sciences. Anyway, so the solid parts of the present land appear in general to have been composed of the productions of the sea and other materials similar to those now found upon the shores. This is what I just read. Hence we find reason to conclude, first, that the land on which we rest is not simple and original, but that it is a composition and had been formed by the operation of second causes. Second, that before the present land was made, there had subsisted a world composed of sea and land, in which were tides and currents with such operations at the bottom of the sea as now take place. The guy is saying, look, this stuff formed in the past, and the past looked a lot like it did today. The same things were going on. I can find these little clamshells in these rocks, and these are the same clams I find out here on the beach. It must have been similar. Lastly, that while the present land was forming at the bottom of the ocean, the former land maintained plants and animals. At least the sea was then inhabited by animals in a similar manner as it is at present. Hence, we are led to conclude that the greater part of our land, if not the whole, had been produced by operations natural to this globe, but that in order to make this land permanent body, resisting the operations of the waters, two things had to be required. So it's basically saying all this land we're on seems to have been formed. Firstly, the consolidation of masses formed by collections of loose or incoherent materials. Let's read that again. The consolidation of masses, let's say that sediment, let's change that word to sediment. Consolidations of sediment formed by collections of loose or incoherent material. Sure sounds like the formation of sedimentary rocks, doesn't it? The consolidation, the clastic material, the detrital material, the sediment collected together. And secondly, the elevation of those consolidated masses, the sedimentary rocks, from the bottom of the sea, the place where they were collected, to the stations in which they now remain above the level of the ocean. These were sedimentary rocks, and now they got lifted up somehow, or maybe the sea level went down. So he came up with that idea, sort of realized, wait a minute, rocks form out of the processes we see today around us. So Charles Lyell kind of ran with that and came up with this idea called, so this is another guy, called Uniformitarianism. Uniformitarianism, which is basically states the present is the key to the past. In other words, what's going on right now is what was going on in the past. Or in other words, the laws of nature are fixed throughout time. That's really the big take home that we've kind of ran with throughout history, is that the stuff happening today also happened in the past and vice versa. This image is kind of neat. It's from a book. So Charles Lyell sort of wrote the first textbook on geology called The Principles of Geology, and he wrote it, I think, in about 1830 or 1833. And this is of a new edition of his from in the 50s that was kind of made its way through the United States. But you can see this is not all that different than the stuff we're seeing in our book. Look, you got this pink stuff, so this is plutonic, so this is the intrusive igneous rocks, so it's like granite and stuff. Then up here it kind of turns into extrusives, they call it volcanic rocks, so this is the extrusive igneous rocks. You've got metamorphic rocks, so this is the stuff that's cooking, contact metamorphism right here because it comes into contact with the magma. You've got aqueous up here. Those are the sedimentary rocks that are being laid down up in the ocean. So really, really similar to what we know now today. So really quickly, as we started recognizing that, whoa, geology is a thing, we were able to observe and come up with this stuff that we kind of still use today. This is not all that different than what we find in the textbook. So that's kind of the history and kind of how it all became about. But let's kind of get back to the geologic part. So, like I mentioned before, we have sort of two different ways to look at the age of rocks. We have relative age and numerical age. Numerical age is putting a number on it. Relative age is basically just saying, you know, oh, this is older than that, this is younger than that. So let's talk about relative age. So there's a number of principles used to determine relative age, and a couple of terms here I want you to know, and I've already mentioned these in class. We've gone over formations. Remember when we looked at these pictures of the Grand Canyon, we talked about what formations were and how you can kind of arbitrarily pick them and sort of name them. And I think somebody gave this right here formation name. This is actually the red wall limestone in real life, but there are contacts between these formations. So if this lighter stuff is a formation up here and the stuff below it's a different formation, this is the contact between them. So that's a contact. And these are kind of the formations themselves. So here are the principles. And these are kind of crazy sounding names, but they'll make sense to you in a second as I go through them. They're just big words to explain stuff that's actually pretty simple. And basically relative age helps us to put things in an order of events. So there's original horizontality, there's the law of superposition, there's lateral continuity, cross-cutting relationships, and then other things. So first, let's talk about original horizontality. All that states is beds of sedimentary rocks that are deposited form horizontal layers, right? This is how I've been drawing it. You looked at sedimentary rocks in class and kind of figured this out. There's also the law of superposition. Within an undisturbed sequence of sedimentary or volcanic rocks, layers get younger from the bottom to the top. So the stuff on the bottom is older, stuff on the top is younger. This stuff was deposited first, this stuff was deposited second, and this is last. So it gets younger as you go up, and it gets older as you go down. Not too big of a surprise. Lateral continuity basically states that horizontal layers will go until they taper out, until they disappear. If you think about a sandstone being deposited, right? Sand is coming out of a river. You've got a delta that's growing and growing and growing, and you're basically growing that sandstone out underneath that delta. Eventually, it can stop, and you'll kind of run into the silts or the clays and the shales, and you stop depositing that sandstone. It sort of peters out and thins out. And then there's cross-cutting relationships, and this is one of the more puzzly parts. The rest really doesn't matter a whole lot. And what this states is a disrupted pattern is older than the cause of the disruption. What? In other words, that which is cut into is older. So let's look over here. Over here we have some sedimentary rocks, and we've got some tilted sedimentary rocks. We've got this little igneous body that's this magma that came in here and hardened. That's probably a granite. And we've got this dike. And if you remember from chapter 3 or chapter 4, igneous rocks, dikes are basically this sheet of magma that'll come up and kind of cut across other things. So let's take this, let's try to figure out of these rocks, is the dike older than them or younger than them? Well, this says that which is cut into is older. So the other stuff was here first before the dike. The dike is younger. But what about this stuff on the top? Well, the dike didn't cut through those, so these things must be younger. They happened after the fact. Imagine if this dike actually went all the way to the surface, right? It wouldn't just kind of keep on going. It would ooze out onto the surface and you get a volcano or something. So these things happened later. There was probably some erosion right here that actually brought it down to this level, and you put sedimentary rocks in later. But that's kind of that statement, is that which is cut into is older. So this is cutting into this other stuff, therefore it's older than that. Then intrusions and faults are younger than the rocks they cut through. There's no faults on this picture, but there's an intrusion. This is a magma intrusion. So it's younger than the rock that it cuts into. So it came in here and cut into this stuff. Therefore, it's got to be younger than them. That stuff existed before this did. Therefore, it's younger. This stuff's older. And then I can ask you the hard question of, well, which is older, the intrusion or the dike? That which is cut into is older. Therefore, the intrusion is older than the dike because the dike cut across it and not the other way. Fun little puzzles. We'll go into more of these things in class where you can actually go through all this stuff, and you know, it's a fun little puzzly thing. So, other relationships, there's big contacts, then there's inclusions, so the fragments embedded in the host rock are actually older. This isn't too important. In fact, I'm not really going to go over it. You can kind of read this on your own, but it's not super important. Basically, if we find these inclusions in this granite, we know that, oh, they're actually older because this granite was an intrusion that cut across this other stuff. It's fairly obvious when you start to think about it. So, other things we get with relative time, we have something called unconformities. So without looking at this stuff, I kind of want you to just listen to this. And what an unconformity is it's a layer, it's basically a contact that represents a gap in the geologic record. And they're kind of trying to show that here with this, but let me just kind of explain it. So let's say we're in the ocean, we're on the continent, you know, we're in shallow water somewhere, and we deposit a sandstone, and we deposit a shale, and then we deposit another sandstone on top of those. All right, now sea level drops. If sea levels drop, we're up on the land, so hey, now we're getting weathering and erosion, and we're beating apart that sandstone, and we're eroding it away. Now the sandstone's gone, and we're going to weather and beat apart that shale. That shale's now gone. We're now just left with the sandstone. Oh, now sea levels come back up. We're back under the water, and now a limestone forms on top of that sandstone. The contact between that new limestone and that old sandstone is an unconformity. That's basically what they're showing here. And in fact, what I just described is a special type of unconformity called a disconformity. We have sedimentary rocks on top of sedimentary rocks. So that contact represents a gap in geologic time because you've lost that initial that shale and that upper sandstone. You lost it to erosion, and so that's kind of what these things represent. So we'll go through. There's three different types of unconformities. There's disconformities, which is what this is. There's angular unconformities, which is basically this, but the rocks underneath are angled. Let's go back to these guys. This one actually. So you can see how these rocks are sedimentary rocks. Ignore the granite, but you see these sedimentary rocks, how they're at an angle compared to this stuff on top. That's an angular unconformity right there. So you had all these things being deposited, then you tilted them up on end, now you eroded it down, and now you deposited stuff on top. This is an angular unconformity. There's also something called a nonconformity. Usually represents a really big gap in the geologic record, or it can. It's basically where you have sedimentary rocks sitting on top of older metamorphic and igneous rocks. So, what about this? So here's this historic Sychar point. I'll go ahead and turn it into drawing form again. We've got sedimentary layers here, right? We've got the those top layers and then the bottom layers. Is this an unconformity? And where is it? It's right here, right? You've got top layers that are horizontal, mostly horizontal, and you've got this other stuff that's at an angle to it. So this is an angular unconformity. Picture, again, like we saw from the beginning of the Grand Canyon, there's actually an angular unconformity on this image. Can you find it? Right there. The stuff in the bottom is kind of coming up at an angle compared to these layers. So everything on here up is all horizontal. The stuff down here is at an angle. So you get an angular unconformity right along this bottom green line. Something else we deal with kind of relative geologic time, or in general just geologic time and and rocks is we try to correlate them. We try to figure out where the rocks layers are kind of traveling underground, or where they extend to underground, not traveling underground, but where they extend to underground. And you can imagine why this might be important, right? If there's a sandstone that's got a lot of oil in it in one spot, I kind of want to be able to track that thing underneath the ground somewhere else, so I kind of have to correlate it to where it goes. And there's a number of different ways to do that, so I can kind of run through a simple version in your head, because you've sort of done it in the past when we looked at this image. So let's take a look at this layer up top here, right? This kind of white layer. Our eyeballs can sort of correlate this, right? I know that this layer is the same one over here. We just correlated that that is the same thing, or that we've connected those together. It's about the same thickness, it's about the same color, it kind of erodes in the same way. And we can even continue all the way across. And now there's this little hoodoo right there. That's probably a piece of it too, right? We can correlate that. Or we can look at the red wall limestone down here and see that it correlates across over here. Pretty simple, right? That's correlation. Really simple to do it in this manner. However, when you try to do it across continents, it can be a little more difficult, or if you try to do it where you don't have nice open canyons like this, but you're just drilling underground, and all the information you have is what kind of came up with your drill, it can be a little bit more difficult to correlate these rocks. So similar example, just kind of in drawing form, we can correlate these sands, you can correlate these rocks going across here like that. That's correlation. Now, the other type of geologic, I don't want to say dating. Geologic, yeah, I guess it's dating. This is numerical age dating and not relative age dating. Numerical age dating is what it sounds like. It's where we put a number on these things. This rock is 1.2 million years old. None of that other stuff we were talking about earlier puts numbers on to things. Numerical age dating is relatively new. We had to kind of discover how to do this kind of in the mid-1900s, or even a little bit later, to figure out how this works. It was something I think, discovered around the 60s. Don't quote me on that. But kind of here's how it works, and it's called isotopic dating. If you remember back, I made you guys kind of remember what isotopes are. I probably put well, I'm not going to say that. I probably put questions on the test about what an isotope is. This is why I wanted you to learn it, because you have to understand what an isotope is in order to understand how radioactive decay works and how isotopic dating works. So remember, an isotope is a variety of the same element that has a different number of neutrons. So if I've got, a hydrogen, it's got one proton, one neutron. If I add another neutron, guess what? It's just a different type of hydrogen, but it's still hydrogen. Now, if I add a proton to that hydrogen, where it no longer has one proton, but two protons, it's now helium, because the protons dictate what the element is. The number of protons make it the element. It's how we define what an element is. So certain isotopes, if they have too many neutrons, they will become radioactive. They will become unstable, and they'll go through decay. And there's different types of decay that they'll go through. Basically, they will radiate stuff. They will become radioactive. And there's alpha decay and beta decay and electron capture. And I'm not going to make you memorize this stuff. I just want you to be kind of aware of it, that there's different types of decay. Alpha decay, these elements will kind of kick off an alpha particle, which is basically a helium element. Right? It's got two neutrons and two protons and two neutrons that it shoots out. There's beta decay, where a neutron emits an electron and turns into a proton, so then it becomes a new element. So if this were to happen to hydrogen and it emits a beta particle from its neutron, all of a sudden that neutron turns into a proton. Now you've got helium. There's also electron capture, where a proton captures an electron and it becomes a neutron. So it actually, the daughter nucleus, which is, the next nucleus after you've gone through some decay, is actually an atomic number lower than what it was before. So instead of like this instance where I get a bigger element, in this one I'm getting a smaller element. So with isotopic dating, we have something called half-life. Before I even launch into that, in fact, I almost want you to pause it right here to go watch another video that I'm going to post on carbon dating, because I think it'll do a really good job of sort of explaining how this age dating works. But essentially, in some a rock, let's just say you've got a rock, you've got a certain number of atoms in there, and let's say you have a whole bunch of them are radioactive. Well, those radioactive atoms will kind of randomly decay. They won't all decay at once. Certain ones will just pop into these daughter isotopes. They'll just kind of spontaneously decay, but the group as a whole kind of changes over time. And when half of all your little atoms are decayed, we call that the half-life. And that's why you hear about half-life a lot with isotopic dating. So one half-life is where the material you have, half those elements have decayed, half those atoms have decayed. Half-life again is where the next half has decayed, and this creates a certain rate, and we can measure the ratios of the old parent isotopes to the new daughter isotopes, and this ratio helps us figure out how many half-lives we've gone through and how much time we've gone through. But go ahead, pause this, go watch that other video I have on carbon isotopes, and radiocarbon dating is kind of the really popular one. It's one you hear about a lot on on TV and pop culture. But go ahead and pause this, go watch that. Okay, I'm going to assume you paused it and that you've watched it now. So let's kind of launch back into this. So you'll recognize that they mentioned that it's only radiocarbon dating is only good for about 60,000 years, and that's because this graph basically just gets too wide. All that carbon-14 sort of decays into the nitrogen-14, and you're just kind of left with no carbon-14, and it's only good for so many years. It's just you can't. If you get into millions of years, all that carbon-14 is basically all decayed, and we just can't measure what's left. However, there are other radioactive isotopes. There's some that are really big, like uranium, and those are the things that we tend to use to date far deeper into time. But what's really convenient with the carbon dating is we can use it on life, right? We're made out of carbon, so it's really convenient. So I can take a bone and I can date that bone as long as it's younger than 60,000 years. But if I've got a bone and it's a million years old, I've got to use something else. And it's a little bit difficult because there's really nothing in that bone that I can use. I sort of have to date the rocks that it came out of and not the bone itself. Again, this is the carbon-14. I'll just kind of leave this here. You can look at it if you want to use it to study. But this is explained better in that other video. So I mentioned uranium. So uranium-238, that's how many protons and neutrons this thing has altogether. It's kind of our main tool that geologists use for radiometric dating. It can be used to date rocks that formed and crystallized from about 1 million years ago to over 4.5 billion years ago, and it's pretty accurate. But what's crazy about it, it's not all that simple. With carbon dating, it's really simple. Carbon-14 decays into nitrogen-14. That's it. One little decay cycle. With uranium, it goes through multiple cycles of decay. It turns into different elements. So uranium-238 goes through an alpha decay, turns into thorium-234. Well, guess what? This is also radioactive. It goes through beta decay, turns into whatever PA is. I don't even know what that is. 234, which then goes through beta decay back to uranium. Now we're at just a different type of uranium with fewer neutrons, and on 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 until we get to stable lead-206. This requires some fun math and a lot of graphing, but if you go through all of it, you can figure out the age of a of a rock that you're dating. Really, what we're dating, especially with uranium 238, is we're dating the igneous rocks. That clock of the igneous rocks, when you have a magma and it solidifies, that's kind of when the clock starts. So we want to use igneous rocks to do the dating. Now imagine you've got a sedimentary sandstone, right? It's made out of quartz grains. It's made out of quartz sand. If I try and go to date one of those quartz grains, I'm not going to get the age of that sandstone. I'm going to get the age of that quartz from where it cooled off and hardened. I'm going to get the age of the granite that it first came out of, right? I'm not going to get the age of that sandstone. So if I want to know the age of that sandstone and when that sandstone was set down, I need to find other things around it that I can date. And usually that might mean a layer of volcanic ash, or, usually that's what it is, honestly. It's the volcanic ash. So over time, we've gotten better at doing this. We found other elements that can help us age date things. How reliable is it? Pretty dang reliable. I mean, we can go get a rock and we can pull up pieces of it and we can date them over and over and over again, and we always get the same results. We can also compare it to relative dating. So I can find a layer of rock, on one side of the Grand Canyon where I know I'm in that, that kind of thicker white rock at the top. I can date it on the north side of the Grand Canyon. I can date it on the south side of the Grand Canyon. And amazingly, I get the same date. And it doesn't change through time. I can date it now. I can date it 10 years from now, 50 years from now. And guess what? We come up with the same date. It seems to be stagnant. These rates of change of these these half-lives of these different radioactive elements seems to be a stable thing throughout geologic time. We don't have any reason to believe otherwise. This kind of deals with what I talked about. Isotopic dating gives numerical time brackets for events with known relative ages. So like I said with that sedimentary rock, I may not be able to figure out the age of the sedimentary rock, but I can kind of constrain it. If I've got a volcanic ash above it and maybe basalt below it, I can date those things and I can say, okay, well this thing is between 50 and 55 million years old because those are the two ages of that volcanic ash and the basalt. And that's kind of what we do with fossils. It's really hard to figure out the age of some dinosaur bone. We've got to go to the nearby layers above and below it that we can date, those igneous layers that we can date to try and help constrain those ages. And honestly, that's why it's really hard. If somebody throws a dinosaur bone at me and says, how old is this? I say, I have no clue because I don't know where it came from. So when you pull a dinosaur bone out of the ground, it's really important to know the ground it came out of. I had a guy who kind of showed me a fossil on Facebook and said, what is this? And I'm like, I can take a stab at it. It's probably this or maybe this. And I was like, if I knew where it came from, I could help you out. He's like, well, I've got the latitude and longitude. I can give you the GPS of this rock or of this fossil. I was able to figure out where it was, figure out what layer it was in, and I could tell him like, oh, okay, this thing's 400 million years old. It's not a trilobite because they were dead by this time, so therefore it's a clam. So don't take fossils out of rocks without taking the picture of a rock and knowing your location. So how do we know the age of the Earth? Well, we have a numerical date for the Earth. And here's the thing about the Earth is this. On the surface of the Earth, all the rocks, there's no rock on the surface of the Earth that's as old as the Earth. We've got this thing called plate tectonics, and all these plates are moving around, and we have erosion. So all the rocks are kind of getting beat up over time. They're getting subducted back down, melted back down. And so we can't really find rocks that are super old on the surface of the Earth. I think the oldest that we found is maybe 4 billion years old. And that may be based on like just a single little crystal. There's something called a zircon, and zircon crystals kind of are really hard to melt and destroy. And sometimes they get reworked through plate tectonics, so they'll maybe survive being melted and get kicked back up onto the continent again. But generally, the oldest rocks we got on the continents, there's some up in Canada that are around 3.5 billion years old, and there's some down in Australia that are like 3.8 billion years old. But if we make the assumption that the solar system all formed around the same time, which is not a bad assumption to make. Then we can date meteorites. And if you date meteorites, almost all of them give the same age. And it's one of the reasons we think the solar system formed at the same time, is because all the meteorites we get, they all numerically date at 4.56 billion years ago. So we think that's about when the Earth formed. And at that time period, maybe the Earth was extremely hot and quite molten, and it took a little while to kind of cool off and actually turn into a rock. But that's kind of where we get that age from. So when you're holding a meteorite, you're holding one of the oldest things on the surface of this planet. In fact, you're holding something that is older than the planet itself. So that's pretty cool. I'll try to remember to bring in my meteorite and show that to you guys, let you hold it, and so you can just be like, wow, this is ancient. So we'll spend a little bit more time on this in class. In fact, I should have already talked to you by this standpoint about how we're going to kind of do a little mini project outside, just to get us outside on a little mini field trip. We have something called the geologic time scale, and it basically allows us to kind of correlate rocks across the surface of the planet, and it subdivides. What it does is it divides geologic time into these different eons, eras, and periods, and epochs even. We use fossils usually to figure this out, and we combine it with numerical age dating, and this is kind of what we use. I'm not going to make you really memorize this stuff. If you were in an honors geology class, I absolutely would. If you go further into geology, this is absolutely something you need to memorize. I can rattle these things off all very quickly in my head. I have a mnemonic device that kind of helps me remember them for several. Well, I can tell you what I use for this little segment. It's cosine DMPP. I just remember that for whatever reason. COS, cosine, right? In math and trigonometry. DMPP. Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvania, Permian. The Mesozoic, I just never forget this because I'm a dinosaur nut. So this is the age of the dinosaurs. Anyway, we'll get more into this in class. Yeah, so that's kind of it for this chapter in geologic time. I'll kind of rattle into. I'll get you guys in class before I talk about some really fun stuff and kind of deep geologic time. And if you get me going, we can even talk about aliens and why, aliens as pop culture portrays them, why they're almost certainly not around, and it has to deal with not only is space vast, but time itself is vast. Anyway, that's all. Let me know if you got questions on Canvas. Yeah, have a good one.